Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Saqif bin Muzamir and my metric number is 211362713. So in this video, I will discuss about LAB2, which is dynamic response of the second order system. Okay, so in this lab, we'll have two sections, which is section A and section B. For section A, we need to derive the transfer function from this circuit, and after done the derive the transfer function, we need apply it to the simulating model and by using coding M file. Okay, so this is a simulating model for the section A. So this transfer function for the section A, we get S over the 0.1 S square plus 2S plus 50. So we put the value numerator is 1, 0. For the denominator is 0.1, 2, and P50. Okay. And we need set the step time to 0. Okay. And click run. Okay, so click the scope for the output. Okay, so this is output from simulating model for section A. So we going to the M5 code. We'll find the code. Okay. So the numerator 10, denominator is 0.1, 2, and 50. G equal to transfer function, numerator, denominator, and step G. Okay, so click run. We need to save the file first. So wait for a while. Okay, so this is output waveform from the MATLAB file. So we can see the output shape is same, but the shape is small different, a bit smaller different, because the time is different. We can see the time from the Simonic model is 10 seconds, and from the MATLAB code is 0.6. So we can see the peak response, transition time, and also the steady state. Okay, so we can see the peak amplitude at 0.257, and transition time is at 0.429 seconds, and the steady state at the final value is 0. Okay, so we're going to the section B. From so we need to change the value. The numerator is 16, 1, 8, and 16. Then click apply, click OK. Okay, so the initial output is 0, and the start time also 0. Okay, and click run. Okay, so click at the scope. Okay, so this is the output for the section B, question A from the Simonic model. So we are going to see the from the MATLAB file. So this is numerator is 16, the denominator is 1, 8, and 16. G is a transfer function equal to transfer function TF. We call back the numerator and denominator, and we use a unit step for the transfer function. Then click run. Okay, so we can see the shape is same. So we can see the rush time, settling time, also the steady state. So the rush time for the graph is 0.84, while the settling time at 1.46, and the steady state happen at the amplitude value is 1. So this is the pole zero map for the section A. So the code is same. We use the PZ map only. Change the step G to the PZ map. Click run. Okay. So this is a pole zero map for a section A, which is in condition critical dam. Why critical dam? Because it is a single repeated negative root. We can see this. Okay, so we are going to the question B. Okay, so we are going move to the question B. Okay, so question B is 16 over s square plus 16. So we put the value for the numerator is 16 and the denominator is 1, 0 and 16. Then click OK, click run. Okay, so click the scope. Okay, so the output will like this shape from the simulating model. So we move to the file code. So the code is same: numerator, denominator, transfer function, and unit step. So click run. Okay, so the shape will be like this. We need to change the limits for the x axis. Click properties. Okay, so click the limits. So we change to 50 and close, and we can also change to the small value for the second. Click properties. So 10 negative 0.5. Yes. Okay, so the graph will be same for the simulating model and N5 code. So we can see the peak response, transient time, also and steady state. So the peak amplitude is 2 because the various amplitude limit is 2, and the steady state value is infinity because the shape will continuous. Okay, so this is the code for PZ map for the question B. So the pole zero map for the question B is in undamped condition because we can see it has a complex conjugate. This is complex conjugate. Okay, so for the question 3, so this is question C for section B. Okay, so put the value for numerator is 16 and denominator is 1, 5 and 16. click OK and run. So click the scope. Okay, so this is graph for the efficiency from the by using simulating model. Okay, so we are gonna to see graph from the M file code. So this is code for the efficiency section B. The numerator is 16, denominator 1, 5, 16. So this is the process for the transfer function. Click run. Okay, so we can see the graph is same shape, but have a small difference because the time limit is for simulating model is 10, while time limit for M5 code is 2.5 seconds. So we can set the peak response, settling time, and steady state. So here we can see the peak amplitude at 1.08 is in a condition of overshoot. For the settling time is at 1.5, while for the steady state happen at the value amplitude is 1. So we are going to the post zero map. This code for post zero map efficiency. Click run. Okay, so for the efficiency, the condition is under dam. Why under dam? Because we can see the pole value is in the complex conjugate. Oh, I'm sorry. For the question B is in condition undamped because it's the per imaginary, no real part. So this is question C. So next, the last question is question D. So we need to change a value, which is the numerator is 20, 1, 9, and 20. Click apply and click OK. Then click run. Okay, so click the scope for the output. Okay, so this is the output for the last question in section B from the simulating model. So we are going to see the M file code. So this is a M file code for the question D in section B. Click run. Okay, so we can see the output graph. Shape is same, but a small difference because the time limit. So we can set the rush time, and steady state. So for the rush time happen at 0.758 seconds, while for transition time is at 1.32 seconds, and the final value for the steady state happen at the max amplitude, which is which is the value for steady state happen at maximum amplitude. The value is 1. Okay, so the last one is the PZMap file. So this is the PZMap file for the question D in section B part. So click run. Okay, for PZMap for the question D, we can see the condition is overdamp. Why overdamp? Because it has two real and negative root. Two real, this is a real part, y-axis imaginary, two real and negative root. So that's all from me. Thank you.